G'day fellow electronics enthusiasts. Today we're diving into a topic that often causes confusion, even for seasoned engineers' ground connections. You see these little symbols all over data sheets and schematics. AGND, DGND, PGND, the list goes on. It can feel like a cryptic language, but fear not. I'm here to demystify these terms and equip you with the knowledge to tame even the most unruly ground loops. Now you might be thinking ground is ground, right? Just connect everything to a common point and you're good to go. Well, not so fast. In the real world of electronics, things aren't always that simple. Different parts of your circuit can have different ground requirements, and failing to address these can lead to all sorts of nasty problems, from noise and interference to outright circuit malfunction. So why all the fuss about different ground connections? The answer lies in the fact that electrical signals, especially at high frequencies, don't just flow through conductors. They also radiate electromagnetic energy. This energy can couple into nearby conductors, including our old friend ground. When different parts of a circuit share a common ground path, these unwanted signals can find their way back into sensitive areas, wreaking havoc on your signal integrity. To combat this electromagnetic mayhem, we employ a strategy of dividing and conquering. Instead of a single monolithic ground plane, we introduce separate ground connections for different functional blocks in our circuit. This helps to isolate sensitive signals from noisy ones, preventing unwanted coupling and ensuring proper circuit operation. Some of the most common ground connection types you'll encounter are AGND, analog ground. This is the ground reference for all your analog circuitry. It needs to be as clean and stable as possible to prevent noise from corrupting your precious analog signals. DGND, digital ground. As the name suggests, this ground is dedicated to the digital domain. Digital circuits are notorious for generating high-frequency noise due to their fast-switching transients. Keeping DGND separate from AGND helps to shield analog components from this digital racket. PGND, power ground. This ground connection is reserved for the high current paths of your power supply. By separating PGND from the other grounds, you minimize the impact of voltage drops and noise generated by current flowing through the power supply. SGND, shield ground. Shields are often used to protect sensitive circuits from external electromagnetic interference. SGND provides a return path for currents flowing on the shield, preventing them from coupling into other parts of the circuit. By strategically separating these grounds, we can create a more robust and resilient electronic system. However, completely isolating these grounds is neither practical nor desirable. This is where the concept of net ties comes into play. Now let's talk about a common scenario where these different ground connections come together. Mixed signal integrated circuits, ICs. These versatile chips often incorporate both analog and digital circuitry within a single package. As you might expect, they have dedicated AGND and DGND pins to keep those domains separate within the IC. Similarly, power regulators, responsible for providing clean and stable voltage rails to your circuit, often feature separate PGND pins. This is crucial for isolating the high current switching activity of the regulator from the rest of the circuit, preventing noise from polluting your power supply rails. But here's the thing, while these separate grounds are essential within the IC, they can't remain completely isolated in your overall circuit design. Imagine trying to measure an analog signal referenced to AGND using a microcontroller referenced to DGND. Without a common reference point, your measurement would be meaningless. This is where net ties come to the rescue. These are carefully placed connections that bridge the different ground domains at specific points in your circuit. Think of them as controlled bridges between islands, allowing for communication and a shared reference point without turning your carefully segregated grounds into a chaotic free-for-all. The key to successful net tie implementation lies in understanding where and how to connect them. A common approach is to connect AGND, DGND, and PGND at a single point, typically near the power supply or the mixed signal IC. This establishes a common ground reference for the entire system while still maintaining some degree of separation between the different ground domains. However, simply connecting all the grounds together at one point can create new problems. Remember those pesky high-frequency currents we talked about earlier? If they're forced to share a single path, they can induce noise and voltage drops, defeating the purpose of separating the grounds in the first place.